Assalamualaikum and a very good day everyone. My name is DAYANG. My group members is AMIRUL, FARIS, SYAHRAIN, BATRISYA and also VEMAL. We are from group 4. We are going to be present about the petroleum refineries. So without further ado, let's get through it. Before discussing about the pressure measurement used in the petroleum refineries, let's first understand why pressure measurement is so important in this industry. When we think about petroleum refineries, we can imagine a very large industrial plant where crude oil is processed into useful products such as gasoline, diesel, and jet fuel. These processes take place continuously 24 hours a day and involve large equipment such as distillation columns, reactors, pumps, and pipelines. Many of these units operate under high pressure. If the pressure becomes too high, it may damage equipment or create safety hazards. On the other hand, if the pressure is too low, the process may not operate efficiently and product quality can be affected. So because of this, refinery operators need accurate pressure information at all times. This is where pressure measurement devices become important. This instrument helps operators monitor process conditions and ensure that refinery units are operating within safe limits. The information provided by these devices is also used for process control, equipment protection, and overall plant efficiency. As refinery technologies continue to develop, pressure measurement systems have also become more advanced. Modern instruments are not only able to measure pressure accurately but can also communicate with control systems and provide diagnostic information to support maintenance activities. Therefore, understanding how these pressure measurements devices work and why are they used in petroleum refineries operation is important for ensuring safe, reliable, and efficient plant performance. With the understanding, let me pass it to the next presenter, SYAHRAIN BATRISYA, to explain more about the pressure measurement devices.
Thank you, Dayang. Moving on, this literature review focuses on pressure measurement within the crude distillation unit of a petroleum refinery. The process begins when crude oil is pumped from storage, preheated, and then fired in a furnace to over 350 degrees Celsius. The resulting vapor liquid mixture enter the atmospheric distillation column where pressure and temperature gradients separate from hydrocarbon by their boiling point. Light fraction rise to the top while heavy residue collects at the bottom. Pressure measurement is critical here because it directly affects separation efficiency, product quality, and overall plant safety. Any deviation can lead to unstable operation, equipment damage, or even overpressure hazard. Across the unit, 11 pressure instruments are installed across 5 process sections, forming 8 distinct pressure loops. At the column overhead, a closed-loop automatic control system uses a pressure transmitter, a controller, and a control valve to maintain a stable pressure continuously. Local pressure gauge allow field operator to manually check key points such as pump discharge and side draw pressure. For overpressure protection, spring-loaded pressure safety valve are installed. Purely mechanical devices that are vent assesses pressure to the flash system independently of the control system or power supply. Together, these 8 loops ranging from simple local indication to fully automatic control and emergency relief to ensure the distillation columns operate safely, efficiently, and reliably. That's all from me. I'm now heading over to the VEMAL for the next part.
Working principle of Bourdon tube. Firstly, when the water passes water vapor or gas passes through parallelly, it will enter the narrow valve of the pressure gauge and it will hit the stem. When the stem hit it will automatically calibrate it and it help to measure the data. And it also sometimes, if the pressure gauge is advanced, it also will convert it into electrical output. Construction of the Bourdon tube. Most of the Bourdon tube have a C head which are sealed in the end and also have a pointer in the middle, and the narrow valve also sealed it to minimize the water or vapor enters the stream. 5 advantages of the Bourdon tube pressure gauge. First, Bourdon tube pressure gauge can give accurate result. Second, Bourdon tube pressure gauge is really low cost compared than the other devices. Third, Bourdon tube pressure gauge construction is really simple. Fourth, Bourdon tube pressure gauge can convert the data into electrical output. Fifth but not least, Bourdon tube pressure gauge have a really simple and safe working environment. Function of Bourdon tube in petroleum refineries. First, Borden tube helps to detect leakage. If there is any leakage, Borden tube works rapidly and it will give signs to the operators. The operators will shut down the plant. Second, Borden tube pressure gauge also helps in preventing explosion. When the pressure increases, the Borden tube pressure gauge work fastly and will bring the pressure to the normal. When the pressure decreases, it also work rapidly and simultaneously and bring the pressure to the normal.
Thank you, Matt, for the excellent breakdown of traditional Borden tube pressure gauge. It's amazing how reliable the classic mechanical system has been for so long. But in modern industrial automation, we need to take the raw physical force and turn it into real-time digital intelligence. That brings us to the unsung hero of the modern processing plant, which is the smart pressure transmitter. It starts at the base with the SOLONG diaphragms. These are metallic membranes, often made from material like alkali, that flex under pressure to safeguard the delicate internal electronic from harsh and corrosive process goods. Right behind them is an incompressible fluid such as silicon or fluorocarbon liquid, which hydraulically channels that mechanical movement inwards. This fluid pushes again the sensing slab, translating the mechanical strength into electrical frequency. You change using capacity for silicon resonance sensor. Up in the housing chips, which is the microprocessor box that acts as the brain to handle the vital tasks like thermal decomposition, analog to digital conversion, and self-diagnostics. Finally, the local display, which is LCD, that provide technicians on the field floor with instant real-time pressure and diagnostic error codes. So, how does the raw physical force actually transform into data? It follows a highly controlled 5-step journey. Step number 1 is force application. The process fluid exerts raw physical force onto the high and low pressure isolating difference. Step number 2 is hydraulic transfer. The internal fluid reliably transmits the exert applied force directly into the central sensing element. Step number 3 is mechanical strain. The sensor experiences physical strain which dynamically alters its natural electrical capacity. Step number 4 is the algorithmic computation. This is where the microprocessor step in, apply real-time calibration offset to completely eliminate ambient thermal drift. Step number 5 and the last step is the digital output. The refined, accurate data is converted into standard 4 to 20 milliamp analog signal featuring superimposed digital HUD protocol to advanced monitoring. So, where do we deploy this digital intelligence? These smart transmitters are utility across the refining system. There are 3 example applications that I list here. The first one is the fluid flow measurement. By tracking the pressure drop across a primary section element like very fast plates, it calculates highly accurate volumetric flow rates for hydrocarbons or steam. The second one is the liquid level monitoring. It precisely measures hydrostatic head in extreme environment like vacuum distillation column, preventing dangerous vessel overflowings or dry outs where all the sensors. The last application, which is the filter fluffing detection. It monitors tiny differential pressure drops across the filter beds to trigger proactive maintenance algorithms, allowing operators to flush out filters well before a costly blood shutdown happens.
Q is, moving on, this section traces the PNID of the crude distillation unit. Crude oil is pumped by P101 to furnace F101, heated to 370 degrees Celsius, then enter column T101. The temperature gradient separate hydrocarbon by boiling point, like vaporized and condensed in 101 and collected in D101. Part returned as reflux, the rest goes downstream. Side product we have here is kerosene, diesel and AGO are withdrawn. Pump around cooler E102, remove excess heat. Bottom reboiler E103 adds heat, while residue exits for further processing. That's all from me. I'm now heading over to the VEMAL. Thank you.
Thank you, Irene. Now we are going to talk about the difference between Borden tube pressure gauge and smart DP transmitter. First, in the term of cost. Borden tube is much more cheaper compared to smart DP transmitter. Second, in the term of maintenance. Borden tube doesn't require high maintenance. Unfortunately, smart DP transmitter require high maintenance and periodic calibration. Third, in terms of safety. Borden tube only provide local safety. Meanwhile, smart DP transmitter have interlocks, alarms, and automatic safety action. Fourth is in the terms of data logging. Smart DP transmitter has automatic data logging. Meanwhile, Borden tube doesn't have automatic data logging and it doesn't have a data logging. 5. Remote logging. Remote logging in Borden tube is not currently available, but smart DP transmitter have SCADA, DCS, and hard communication systems. Now we are going to talk about the evolution of pressure measuring devices in petroleum refineries. First, in 1940s. In 1940s, they usually use the manual pressure devices such as Borden tube, which doesn't have special specifications. Second, 1950 to 1916. In the 1950 to 1916, they start to introduce electrical, which have some of the electrical output system. Third, 1970s to 1980s, they start to introduce the automatic system where automatic calibrations are available. For 90s, in the 1990s, they start to have key features such as HRT protocols. After that, 20s to 2090s era. In the 2090s era, they start to introduce the SCADA, DCS system, and real-life monitoring and much more. In previous system, which is 2020 to 2026. Now we have really smart DP transmitters and analytic predictive system, which are much more advanced.
In the high-stakes environment of a petroleum refinery, pressure is the invisible force governing fluid flow, separation efficiency, and overall plant safety within the atmospheric crude oil distillation unit. Our analysis highlights a vital engineering principle, where the highest level of operational reliability doesn't come from replacing old technology, but from combining it with the new. On one hand, we rely on the traditional Borden tube pressure gauge, where it is a robust mechanical sentinel that requires zero external power for local field verification. On the other hand, the smart differential pressure transmitter serves as our digital nervous system, feeding high accuracy, real-time data directly into the distributed control system to power Industry 4.0 automation. By aligning these technologies under rigorous API and ASME standards, we create a redundant, highly reliable ecosystem. Ultimately, this integration bridges the gap between field-level resilience and automated intelligence, ensuring optimal production while mitigating operational risks.